everybody. It's Frédéric Klopp. Thank you.
Okay, thanks. So we'll just go on and try finishing what we were up to prove. So remember, we were looking at the thermodynamic limit n, right, and wanted to prove that actually this rho subject to S over n going to sigma converges to E rho sigma, and we had already done this for some special subsequence. So the main game will be to bring ourselves back to the subsequence, and of course the only tool that we essentially have is these subadditive inequalities. So we are going to use this extensively, and we are going to split the proof into two steps. First, an upper bound, and then the lower bound. So the upper bound is just, we're going to prove that the lim sup of this sequence is bounded by this quantity. Right. And of course, if you prove that the lim in from the same sequence is bounded by the same quantity, will be done. Okay, so therefore what we do is, so rho now doesn't have the special form, so we pick rho 0 larger than rho, so that we can use the monotonicity, right, of the form rho 0 equals n0 2 to the n 0d L tilde to the d. For some little n0, large n0, right, that are going to be large but fixed in n squared. Okay. So of course this is not unique, but there is a minimal one, right? So we can, so this is not unique, but there is a minimal one. So we define minimal in which sense? Minimal in the sense that n, this integer is minimal. So we can write rho 0 as n min So essentially you remove from an n0, you remove all the powers of 2 to the d, right, coming up inside the prime decomposition of n0. N is minimal. Okay, and now what we do is we split. We're going, so keep the n0, but we introduce this n minimal. And now we have the number of particles. We just do the Euclidean division of the number of particles by n0. N0, right? And we are going to split the cube lambda. Actually, we're going to find inside the cube lambda cubes of a size large L n0. Remember, there was a formula for large L. I'm going to put it on the board. So for this, we choose n0 large, right, as a function of n. Okay, so it's going to go to infinity, such that, so you remember we had defined this length. I'm going to recall its definition. This one to the d divided by n goes to 0, but this one we use the fact that in the tempered assumption on the interactions, the power is larger than dimension. This one goes to infinity, and you remember we had defined ln0 to be, well, ln to be 2 1/2 L tilde times 2 to the n minus theta n r, right, integer part. So we now choose for n, each n, we choose an n0 that is large, and such that the two sequences n0 and little n satisfy this condition. Okay, this can be done because, well, lambda is larger than the dimension. Okay, and now if you take for lambda large, you can choose m cubes, right, inside lambda, find m cubes, so it's this m of size Xi times ln0, so side length Xi times ln0, where Xi is chosen between 1 and this, right? Okay, and so it's larger than 1. And in particular, using these cubes, what you do is you shrink the cubes. So these cubes are slightly larger, right, than the ones we are interested in, meaning the ones with side length ln0. So what you do is inside each of these cubes, you put a smaller one. Right, so you have your big thing. This is lambda. Here you put the small cube and these. Okay, and now we're going to shrink them slightly to bring them back to the right size. But the effect of shrinking is that it guarantees that the distance between the cubes is at least the distance from the external boundary, from the boundary of the small cubes to the exterior of the mid-sized cubes, right? So what we do, this guarantees that we can lambda contains m translates, contains lambda, what do I call it, n0 of I, so these have side length ln0, which are m translates of lambda n0 at mutual distance at least Xi minus 1 ln0, right? Just because the distance you gain to the boundary. Okay, so this is Xi ln0 and this is ln0, right? So just because of that, and now you use the subadditivity, which tells you using the S lambda n, using the fact that it's non-increasing in the domain, right? 1 to m minus 1. So why do I explain this in just a second? Sorry. E omega lambda, S over m minus 1 lambda n0 I n0, right? And so I just took m minus 1, and the last one, so I didn't take, you see here you have exactly m minus 1, m n0 particles, and in the last one I'm going to put the remainder, m minus 1 times n0 particles, I included here, and in the last one I'm going to put, well, this to 0, but I'm going to put the number, so this one, of particles equal to, n0 plus r0. Right, and of course I have my error term, which is r0 times n squared psi minus 1 to the minus lambda, right, n0 to the minus lambda. Right, so what I do is, in most of the cubes I put exactly n0 particles corresponding to this decomposition to the Euclidean division, and I keep one cube where I put more particles, right? There'll be a remainder. And essentially what I prove is that this is going to be bound by something depending on n0, okay? And this one will give you the correct convergence. Why? Because we already know that we have convergence not only on this special subsequence, but also when we let the entropy per particle converge to a given number in any way, right? So we're going to use this to get the convergence for this term, right? And so to deal with this term, so now I'm going to explain how to deal with this term. So to deal with this term, what you do is you take this cube, right, and divide. You're just going to use a rough bound actually. You're going to divide lambda n0 m into cubes of size into what do you call it? Yeah, n0 divided by n min. So remember, n0 goes to infinity, n min is fixed. translate. So it translates of lambda L in lambda n min of lambda n min, right? Which will give you the following bound. So this is E omega, which will give you the following bound. So how many you have? G1. So here we have 0, lambda n min j, right? And here we have j. And so this decomposition is again a decomposition of this number in the same way. You remember yesterday we had the decomposition, we had the number of particles, and we wrote it as a sum of integers taking possibly two values, right? And so here we decompose this thing again as a sum of numbers of particles on each of these cubes in such a way that this sums up to that, right? Which can be done exactly in the same way as we did it yesterday. So just require that this sum here is equal to that, and you put roughly, so all the RJs are less than n min. Okay? You dispatch them more or less equally in all the cubes. Okay? And you have the remainder term, which is R0, sorry. 2n0. And you have the sum. So this sum is, of course, because this thing is done, right? This quotient is a power of 2D, right? This quotient is a power of 2D. So you do it step by step in divisions by 2D, right? And every step, you get one term of this sum. Okay, remember, the way to divide this cube was done as yesterday, first generation. So you have a first generation. Then in there you have a second generation. And at every generation you get one of these remainder terms coming out of the subadditive estimate. Okay, so this is where this sum comes from. And this is 0 minus 1. And you have 2n plus 1 d times Rn to the minus 2. Okay. And now this term, oops, so we have this term here. Well, this one is, here n min is a fixed number, right? So you bound it by some constant, depends on n min, but essentially you can bound it by c n min squared, which is roughly, you have a bound, right? Because you have the ground state for the free operator, which is constant times n min, right? Because you have free ground, meaning for non-interacting ground state, okay, you have constant times n min. Why? Because you have n min particles. Okay, yeah, one thing I said it, but I didn't write it, is that Rj here, the Rj's are taken between n min, so you have at most two n min particles, right? And then the interacting term, you just bound them individually, right? And write assumptions on your potential, the assumptions that you put on the interaction potential, means that the bound is given by the square of the number of particles, right? Which is constant times n min square. Okay, so you get a very simple bound on this. But the only thing you're interested in is the fact that this is a bounded quantity, right? What the bound is going to be irrelevant because we are anyway going to divide this by n, right? So this is going to go away. Okay. Find the bound of that type. And if you now plug this into that, and so you plug this bound in there, right? Compute the sum, you get that E omega of 0 lambda n0 m n0 plus r0. So remember, even though it's called n0 and r0, this grows, right? These are things that grow to infinity because, well, of the definition of large n0, right? Large n0 goes to infinity where else? So little n0 goes to infinity at the same rate, at the rate 2 to the large n0d. Okay, and this, you go to the following bound, you get that this is bounded by a constant times n0 times n min. right? But the n min is fixed, so it doesn't really matter. Finally, if you plug this into the other one, divide by n, you get that E omega S lambda n divided by n is bounded from above by n0 divided by n, the sum I going from 1 to m minus 1, 1 over n0, E omega S divided by m minus 1, lambda n0 I r0, right, plus this bound n min divided by n, plus what we had is a, r0 psi minus 1 to the minus lambda, and n divided by L n0 to the lambda. Right, you get this? Okay, and now we are finished. Why? Because we know that by our assumption, by our construction of n0, where is it? It's hidden here. We know that this term goes to 0. Right? We know in the same way that this term goes to 0. That's the same thing. We know that each of these terms, they converge, right? To what? Well, sorry?
Why does this term go to 0?
This goes to 0 because the difference between n0 and n, right? n0 is...
sorry, but in the left blackboard, we write that L over n goes to 0.
Yes, that's correct. But this is, you see, this is, okay? This is, because n0 is proportional to ln0, right? It's because I have density of particles.
Yeah.
So this is why this goes to 0.
I'm sorry, excuse me.
So if you want this, I could have written as n0 divided by n.
Excuse me, sorry.
Okay, no problem. Now, s over m minus 1, right? What is this? M minus 1. This is also S divided by N times N0. Let me think. This, get it quickly. So this is N, M minus 1. So this is S. Let me replace M. So this is N minus R0 times N0. Yes, R0 N minus 1, right? So it is, no. What do I want to do? What I want to check. Okay, yeah, sorry. So this is S divided by that, sorry. What I should do, I want to compute, this is not R0, this is N0, right? What I want to compute here is what is the entropy per particle of this one, right? But the entropy per particle is this, right? Which is exactly Sn, 1 plus little o of 1, right? So it goes to sigma. That's the only thing. Okay, what I need to do is to compute the entropy per particle. I have only N0 particles, right? But the entropy is smaller than in the first, in this right-hand side, right? I just kept the entropy per particle fixed when I dispatched the particles in the different boxes. Okay? And so in this thing, the entropy per particle is going to sigma as well. Okay? The density, well, it has been done in such a way that it goes to rho, 0. Okay? And so this thing, when L goes to, or when lambda goes to infinity, converges to what? To E around rho sigma. Okay, by the theorem that we already know. See, we have the special sequence, right, that we studied, but we have an entropy that converges in some arbitrary way to the number sigma. Okay, and well, we are done. Okay, just do this and that's all. Okay. The number of terms here is proportional exactly to, well, here we could get m over n0, this, and it goes away. Okay. Just as averaging. Okay, so this settles the upper bound, and now the lower bound. Now we want to prove limit of E omega S lambda n, right, divided by n is larger than E rho sigma. And what we're going to do is we're going to use the upper bound that we just proved in the following way. What the idea is just the following. We take a cube, so maybe larger. We take a cube, say, well, it doesn't look much more like a cube, but okay. Lambda, okay. No, this is, lambda is here. Lambda. We take a cube lambda n, which is going to be larger, right, containing lambda. And what we're going to do is we're going to say, well, we know that the entropy, right, on lambda is lower bounded, the entropy on lambda plus, so we take now a boundary, so it's a color choke. I take the exterior, right? So let me say lambda is the exterior. Okay, I take the exterior. So what I'm saying is that by the subadditivity, the entropy on lambda is bounded by the entropy on lambda n minus the entropy in the green region. Not the entropy, sorry. This quantity, okay, subadditivity. This quantity, so the energy, right, in lambda is bounded from below by the energy. So what I want to say is that I write it, it's going to be clearer, as lambda n is going to be bounded from below by E omega S. So I have to say how I divide it. Lambda n minus the entropy in the green region. So what's the name of my green region here? So that I keep the same. So we have S minus Sn, lambda double prime, n minus nn. Right? This is going plus error terms. Plus error, right? And now, what I know is that if I divide this by n, or rather said by this difference, it converges, because we already proved the upper bound, or we already have the upper bound for the limb soup, right, for a general region. Okay? And so from this, I can get the lower bound here. Okay, that's the idea. So to make it precise, So what you do is we construct an admissible cube, right? That contains lambda prime, translate of lambda at distance larger than r0 from lambda, and such that this is going to be less than 2, right? Sorry, 1/2. Okay, so you take it, but not too large, right? Don't leave too much space. How much space is not going to be too important. And now you pick row 1, close to row, admissible, so we're going to pick it of the following form, 2 to the minus q times p, right? And so if for n prime d larger than q, we can of course, as usual, rewrite row 1 is equal to the minus n prime d times n1. n1 being an integer. Right, p is an integer here. Q as well. And we consider, define lambda double prime. These are just the points in the big lambda n prime, as I said, such that the distance of x to lambda prime be larger than theta n r0, right? And now what you can check, which is more or less obvious from the picture, is that if lambda goes to infinity in the Fisher sense, this implies that this one also goes to infinity in the Fisher sense. Right? It's going to fill up the whole space in this regular way. And moreover, you can compute that if I look at lambda plus lambda prime, the two volumes, well, they essentially fill in lambda n prime, this goes to 1, as lambda goes to infinity. Right? There's not prime, but double prime sum. This one. Right? This is because the region here is very small, right? We leave something very small, much smaller than the ln that we had in the beginning. And then you use the subadditivity bound in the way I explained before. So subadditivity yields that if I look at E omega 2 n prime d sigma, that's correct, 2 n prime d sigma on lambda n prime 2 n prime d rho, what is it? Yeah, rho 1. So this is the number of particles, this is n1, right? This is going to be minus E omega 2 n prime d sigma minus s lambda double prime n1 minus n. This is going to be bounded from above by, well, the quantity we want to lower bound plus some remainder term, which is r0 n1 squared theta n prime r0 to the minus lambda. And now if you divide this by n, right, dividing this by n, of course, you get that the limit of E omega s lambda n divided by n is going to be larger than the limit. So this term goes away, right, just by comparing this size to the size of ln. To the limit of what? Of, on the one hand, what you have is, so this one, so this is, we can rewrite as n1 divided by n, and we have E omega of divided by n1, and here we have 2 n prime d sigma lambda n prime n1, okay, minus, and here what do we have? We use this, right? We use this to get that we have, so this one contains n1 minus n divided by n 1 over, so we use this, right? Oh, sorry, we use this formula to replace the number of particles that is inside here, right? So, and let me call it n2. No, so n2 is written somewhere explicitly. Yeah, it's n1. So it's just n1 minus n. Just write it in this way. It's going to be easier. E omega 2 n prime d minus s double prime n1 minus n. Okay, it's just this. So we just remove the remainder term. And now, in the first term, we're on the special sequence. So if you fix epsilon positive, for any epsilon positive, right? In the first term, we're on the special sequence. So when computing this limit, we may replace this one. You compute just the density and the entropy per particle, and you see that these are equal to rho and sigma respectively. And the limit gives you 1 minus epsilon, right? Because we know that this thing on the special subsequence has a limit, right? And the limit is this, so we just lower bound by this. And on the other one, we do the following. Well, we use the upper bound on the lim sup of this one that we just obtained, right? So we can replace this by 1 plus epsilon, and this for any positive epsilon, right? I think there is this is minus. Okay, this is my sign. I was wondering where the sign mistake was. Forgot the minus here. It's not the plus, right? It's the minus. It's here. Okay, and you see what happens. You get that this is thus. So these terms go away. n1 divided by n is bounded, right? n1 divided by n is bounded, and you get that this is larger than epsilon rho sigma minus the constant divided times epsilon, where the constant is a universal constant times the sup of n1 divided by n, which is something bounded. Right, you just do the computation. And for any epsilon, so you get the lower bound you're expecting. Okay, so this finishes this proof. And also what you're going to say about the general systems for the convergence. Okay, so there's a few remarks I wanted to make. So the first remark is that here we just had convergence in L2. One can improve this. Better convergence in the sense that, for example, almost sure or in L1. So of course it would suffice to take a subsequence, right? L2 convergence implies almost sure convergence if you take a subsequence. But what you can actually prove is the following thing. If the interactions have compact support, then convergence is almost sure and in L1, right? So if you take compactly supported interactions, meaning that the interactions go only up to a finite range, then you get convergence in L1 and almost surely. Okay, but I mean this thing about convergence, okay, you need it just to have objects that are properly defined. But what is really interesting, what we really want to do, is to understand what's going on. What is going on for this functional and for the ground state, or for example, for this functional at sigma equals 0, meaning for the ground state energy per particle, and for the ground state. So is there a way? So the problem is compute E rho sigma, right? Can we compute E rho sigma? And understand, one of the basic questions is understanding what's the effect of interactions on your particles, okay? So to understand what is the effect of interactions on the particles, the first thing is you have to know what's happening for the free particles, right? So let's start with the free case. Free particles. So here, to understand, so this convergence was something general which does not depend on the statistics, right? But what happens exactly to this functional, this will depend on the statistics. Okay, this will depend on statistics. So we have to choose a statistic, and the statistics I talk about is fermions. So Fermi-Dirac statistics. Okay, Fermi-Dirac statistics. So let's do it for a bona fide operator. So we look at h omega. I'm going to put it 0 here, so to remind you that u is 0, which is just h omega lambda tensor 1 plus 1 h omega lambda, and h omega is your favorite Schrödinger operator, right? They say a random Schrödinger operator, so h omega is ZD ergodic Schrödinger operator on RD, right? Well, and we want to understand what is, so we are just looking at the ground state energy and the ground state. Well, because the particles are not interacting, this is actually quite simple to do, right? You can actually write out. So let's call, let me look at, so h omega of lambda, and let its spectrum be E1 lambda omega, E2 lambda omega, E. Okay, and associated eigenfunction phi 1 lambda omega, and so on. Okay, so that's the spectrum of your Hamiltonian for one particle. So from this spectrum, you can actually construct the spectrum of H0 omega n, right? So what is it given by? So what is the spectrum? Spectral theory of H0 lambda n. Well, it's simply given by the following thing. The eigenvalues the eigenvalues now will be indexed by n tuples, what do I need? Yeah, I need n tuples. So I pick k1, kn, which belong to n star to the n, and I call this k bar. And I can take e k bar lambda omega is just the sum for j going from 1 to n of e k sub j, right, of lambda omega. And here, of course, I assume that the eigenvalues are repeated according to multiplicity, right? In this, when I write them out, when I enumerate them, I repeat them according to multiplicity. And this, you can check that this energy is an eigenvalue associated to the eigenfunction big phi sub k bar, which is just the antisymmetric tensor product of phi k j, j going from 1 to n, right, of the eigenfunctions for the one particle model, which is also in physics called the Slater determinant. So this is just 1 over n factorial square root, normalizing factor, times the determinant of the matrix phi kj lambda omega at the point xi, right? So this is taken at x when I and j run over 1 to n, right? So you have this matrix. Okay, you have two indices, one in the eigenvalues, one in the variables. You form a matrix out of this, right, in the following way, and take the determinant of this matrix, and you normalize it. And this actually, it's easy to, so first it's totally antisymmetric, that's a property of the determinant, right? And one can check that it's an eigenvalue of this system. Okay, because you put, just look at this, let's say that this is what is it? It's the colon index, right? So that's I is colon index, and you see that On the first column, it's this operator that applies. On the second, it's this one. Third, it's this one, and so on. And the last, it's this one. Okay, because you have the xi in all columns. So, and you just use the multiplilarity property of the determinant, and this gives you this. So we know exactly not only what the ground state is, but also what all the eigenvalues and what all the eigenvectors are, right? But of course, these, well, are rather complicated objects, as we're going to see in a second. Okay, now, what does the ground state energy of our system look like, right? Let's try to compute E of rho sigma. I'm going to put a 0 here to remind you that there is an interaction potential, which in this case is vanishing. Okay, and sigma is 0 because I'm looking at the ground state energy. Sigma is 0. Ground state. Okay, well, from this one, the way to go to get the smallest eigenvalue is, of course, to sum up the n first eigenvalues, right? The infimum of the spectrum of h omega 0 lambda n is given by the sum for j equal 1 to n of ej lambda omega. Right? To get the smallest value here, well, you have to take the smallest value possible here. So you have to take the n first ones. Okay? Now we can define for the random operator, we can define its counting function. Right? So we get that. So this is what I call, let me call it E, to keep my notations as before, E0, right, of lambda and n. And so E omega 0 of lambda and n divided by n. What is this? This is just the sum divided by n, but you can rewrite it in the following way. It's 1 over n integral from minus infinity to E n lambda omega, right, of d large n lambda omega of E, where this is just a counting function for the operator h omega, right, where n lambda omega E is just the number of eigenvalues. So actually what I'm going to do is I'm going to multiply and divide by the volume. It's just the number of eigenvalues of h omega lambda less than E and divided by the volume, right, to take care of this factor.
What about if one eigenvalue of multiplicity bigger than 1? It's not a problem for you when you define.
I agree with you. I agree with you that if you have multiplicity, right, but well, you can always I agree with you. That's correct. That's correct. In this definition, right, you need to be a little bit cautious, right? And this is going to, I agree with you, this is going to work easily if this is simple, right? But if you have multiplicity, what happens is that you just need to understand that the jump of multiplicity, right, is little o of the volume of the cube, right? And you just need this because you see, when you have, imagine that this has some multiplicity that is little o of the volume of the cube, right? Then you can just go a little bit backward and this little o is going to be taken care of by this. Okay? So it's not going to be a real problem. Okay, but I agree with you. I agree with you that there may be a jump like this. And because you, in a cluster of eigenvalues, right, you may have to stop somewhere in the middle to get the nth one. Okay, so whereas this one, this counting function doesn't see that. But let's make it simple. Well, and there's another point. Yeah, there's another point you can make. It's not very difficult to prove that for many random systems, right, if the parameters vary continuously, the eigenvalues, when you fix the cube, are simple. There are no multiple eigenvalues. Right? Typically, what you use is just the fact that, for example, if you look at the Anderson model, you just look at, you just consider, you just reason as follows: the Anderson model depends analytically on the random parameters, right? And so, if you have a continuous probability distribution, okay, the probability that eigenvalues are multiple is going to be 0. Okay, on a finite cube.
Or 1.
Why 1?
Analytically.
No, yeah, okay, it's going, you're right, it's going to be 0 or 1, but for these models it cannot be 1, right? If you send things to infinity, but it's going to be 0. This is really what you proved. Okay, so actually in most of the models we can analyze, we actually can prove that the eigenvalues for a finite cube are almost surely simple. Okay, so the problem actually does not arise. But the only thing that you need is that a jump of multiplicity, right, is going to be little o of 1. Okay, and this actually will come from something else. I'll comment on this a little bit later. Okay, you do this, and now imagine now, and actually this is warranted by the fact that the operator is z-ergodic, it's well known that this quantity converges to what is called the integrated density of states of your operator. Right, this quantity converges to the integrated density of states. Moreover, these functions are obviously non-decreasing functions of energy, right? So if you know that the integrated density of states is a continuous function, you know that this convergence is going to be uniform, right? Well, and there is a recent result by Bourgain and Klein that actually proves that for, at least in dimension 1, 2, 3, if you take continuous random models, right, the density of states when it exists is a continuous function, right? So you have uniform convergence. Okay? So now the idea is just the integral using this increasing convergence. Well, you want to replace this by density of states. You need to find what does this converge to, right? So how is this defined? Well, this is just defined in the following way. What is En lambda omega, at least if it's simple, we come back to the same problem. It's just given by n lambda omega at this value is equal to n. Right? And so if you divide, n divided by lambda. Right? It's given n divided by lambda. And so, because of uniform convergence, because this function is non-decreasing, right? If you go here to the limit formally, what you get is n of e rho, right? If you know that this converges to e rho, this should be equal to rho, right? If you go to the limit formally, when lambda goes to infinity, you get that if this has a limit, then the limit must satisfy this equation. Okay? So there are two possible cases. This function is increasing. Well, the problem is that just the increase of this function doesn't guarantee that you have a unique solution to this, right? The function could be flat at some point, right? And so what you need to do is just, these points are corresponding to gaps inside the spectrum of the random operator, right? The portions where the density of states is flat. So what you do is, well, it depends now on what's happening to this energy. You look at this energy, right? And imagine that it is inside the spectrum of the random operator, okay? And then, well, you can indeed, the proof is here, you can, just by the fact that n of e is strictly increasing at this energy, because you're inside the spectrum, right? You know, and the monotone convergence, you know that this equation implies that En converges to e rho, right? If you are inside the gap, so let me just picture the density of states. So for example, there's something that starts here, does something like this, has a plateau here. If you pick your e rho so that it be here, right, what you're actually going to converge is to this point, right? Because you have many solutions to this equation, because density of states is constant, all the region here, so you need to pick one solution, okay? So this is just done by a limiting procedure, by taking some infimum, right? To take the smallest solutions, right? Take the smallest solution to this. Because you know that in here, there won't be any spectrum, right? You know, in here, there won't be any spectrum for the random operator restricted to the block, right? The spectrum will be restricted to some small region around here, if this is a gap. So imagine that the spectrum of your random operator is purple bands, right? When you restrict the operator to a finite volume, what you'll see is that the spectrum will be within the yellow. Its spectrum is going to be within the yellow bands, right? And so if you count n eigenvalues, the way you're going to hit is down here, right? By this equation. Okay. And so once you've done this, what you get is just the following. So you just define E rho to be the infimum of all the energies such that n of E equals rho, right? And then you show, so we assume that the density, assume n of E continuous, right? Assume that n is continuous, and then you show that E, what is it? E n lambda omega tends to E rho omega almost surely. And when you look at this integral, just use monotone convergence theorem, you get that E 0 omega lambda n divided by n converges to, well, by definition, E 0 rho, which is 1 over, so here we get 1 over rho, integral from minus infinity to E rho, right? And, sorry, there's something missing here, forgot the energy. This would just be the counting function, right? What I have is I have to add the energies, right? So I need to integrate the energies. dNE, right? So we have an explicit formula for E rho, E0 rho, in terms of the spectral data of the one particle operator. Okay? And if you look at what is happening to the ground state eigenfunction, so now we know that if we ground state, the ground state, so this is, let me call it psi 0 lambda n. We know that it is just made of phi 1 lambda omega tensor phi n lambda omega, right? So of course the ground state is a function of many variables, and this is something you can take out of it, right? When you increase the size of the cube and the number of particles, it's the number of variables is going to increase. Then we are going to compute. So this is why we want to compute the marginals, right? What are the marginals? So meaning the K density matrices, right? So I'll just do it for the one density matrix. So remember, one density matrix, what is it? So gamma 1 psi 0 omega lambda n. Well, so this is just, it's a trace class operator, right? Acting on L2. So this is trace class. So I identify the operator with its kernel. And so it's a positive trace class operator on L2 lambda, and which is given by what? Which is given just, the kernel is given by I to n phi I lambda omega at x z bar times lambda I going from 1 to n phi I lambda omega at y z bar, and this is, yeah, the bars do not denote the same things. Here you take the complex conjugate, d z bar, and this is over lambda to the n minus 1, right? And I have to normalize this. What I want is I multiply by n. Why do I multiply by n? Because I want the trace of this operator to be equal to the number of particles, right? Well, this can be computed, right? You just write out the Slater determinant. you can compute this, and what you see is that this is nothing but the sum for I going from 1 to n of phi I lambda omega at x, phi I lambda omega at y bar. So what is this kernel? That's just the kernel of the spectral projector for the one body operator, right, one particle, onto the ith eigenvalue. Okay, so this is just, you look at the spectral projector up to the nth eigenvalue, lambda omega, right, of your operator h omega restricted to lambda, right, at xy. It is just this kernel. Okay, and so this converges, right? You can show that this converges to the spectral projector. To the, oh yeah, one thing I didn't say is that this thing is called the Fermi energy. So this converges as lambda goes to infinity to the Fermi to the projector to the Fermi energy of h omega of the whole operator, right? And the convergence, then it depends what kind of convergence you want, but for example in the strong sense, right? Because these are operators. Right? Okay. So you see what this is. So if you look at the two particle density function, right? It's going to be more complicated, but it's going to be the same thing. So if you look at the gamma 2 psi omega lambda n, well, or gamma k in general, this will be, right? So these x and y now, they are in k variables, right? So this was in just one variable in lambda. This is in k variables, meaning that this is in lambda to the k, this is in lambda to the k, right? And in both of these variables, the thing is anti-symmetric now. Okay? So here there is a normalizing factor depending on n and k, and you take the same integral, psi 0, just to remind you of the definition. Well, let's forget about the lambda and n and so on, they are in there, right? And you take x, z, psi 0, y, z, so z bar, z bar, and this is now over lambda to the n minus k. You integrate this over lambda to the n minus k, right? You perform the same thing, and what you see is that this is equal to the sum of all k tuples, right? So you take I1 less than I2 less than IK between 1 and n, right, of phi I1 wedge, and J1, yeah, no, this is correct, I think phi I1, so wedge J going from 1 to K, phi IK, I read it in this way, as I put, so this is at X, and the same thing, K phi IK at Y bar, right? So this is the sum over all the groups of K fermions that you can form for the n first fermions. Okay, this is what you get. Maybe let me just. Okay, and you see that now. Okay. One thing I wanted to point to is that even though you can compute these objects are already quite complicated, right? These objects are already quite complicated because, well, because of the structure of your random Hamiltonian, right? It's because the eigenfunctions of the one particle Hamiltonian are already quite complicated objects. In particular, imagine, so what we want to do, as I said, what we were interested in is looking at interactions.
Frédéric,
Yes?
do we have a simpler expression like the indicator? What is K?
Well, it's more complicated. You need to rewrite it. You cannot do it just simply in terms, I think, of the one particle Hamiltonian, right?
Okay.
You have to recompose it. But to be frank, I didn't try to work it out actually. So
Say for K equals to 2.
yeah, for k equals to 2, let's think. No, it's not clear that you can do it in such a simple way, because you see, for k equals to, you cannot just use, for example, 2 copies of your random Hamiltonian, right, on some, on the tensor product of 2 parts of the space, because it's not going to be a spectral projector, that's for sure, right? It's not going to be written as, there is a mixing coming from the fermionic nature, right? So it's not just going to be something like an anti-symmetric tensor product of these things by themselves. That's not going to work. Okay, it's going to be more complicated than that. Yeah, it's going to be more complicated than that. Okay, so there is no, just because of the symmetry of fermionic systems, right, you already hit into problems in that kind. But nevertheless, so what I want to say is, if you want to add the interactions, right, h omega u lambda n is just going to be h0 omega lambda n plus the sum u xi minus xj I less than j n, right? If you want to add the interactions, and you want, let's do something very simple. Put the perturbation parameter, epsilon, and assume that epsilon is very small, right? And try just to do simple-minded perturbation theory, right? Just first order or second order perturbation theory to understand what's happening. Okay? So what you need, if you want to understand so first order perturbation theory. Well, we know the shift of the, so if you look at to first order, right? If you look at, let me call this EU, and let's put epsilon here, right? E epsilon u. Sorry, let me take the same notation as before, except that I put a u instead of, so look at this, epsilon u, lambda n, right? It's of course going to be 0, the 0th order, plus epsilon, and what you get next, well, this is just first order perturbation theory, you get the sum of I, j, n, u of xi minus xj applied to the ground state of the free thing. 0, right? This is just this potential applied to ground state plus error terms, right? Of course, O of epsilon squared. So here I take epsilon. For this to be correct, I need epsilon to be actually much smaller, right, than the spacing between the first 2 eigenvalues. So it means that epsilon for this computation to be correct, of course it's going to be correct in some range of epsilon, right? But for this term to be really that small, to guarantee this, I need really, for this one to be the principal term, right? I really need epsilon to be much smaller than the spacing between the first 2 eigenvalues of the total operator. But this spacing is very small, right? Because you look, this spacing is, we know what it is. Here we have the eigenvalues written explicitly, right? How do eigenvalues of a random system behave? Well, here, how many eigenvalues you take? We know that lambda is equal, or sorry, n is equal to rho times lambda, right? So you start, imagine that the bottom of the spectrum of the random operator is 0. Okay? Here you have the Fermi energy. So the nth energy level is going to be, the En is going to be somewhere around here, right? And you're in the bulk of the spectrum. But it's known that in the bulk of the spectrum, the spacing between eigenvalues, right? The spacing between the eigenvalues is 1 over the volume lambda, right? Roughly. So when you go, so what is the next eigenvalue from the when you start from the ground state, E0, well, essentially what you need to do is you need to replace one of these by something else, right? So the best choice, not to go up too much, is to take the largest one and replace it by the next in the list. So the spacing is going to be of that size. Okay? So the spacing here is going to be very small, which means that such a computation is going to be correct only for a really very small epsilon, which is not what you're interested in. But even if you're doing this, what you need to be able to understand is this thing. Right? But this thing can be computed, this integral. So this is computed. Because these are totally anti-symmetric, it's the same thing as n minus 1, right, over 2 times, so the epsilon, of course, times what? Times the integral of u x minus y. And here you have psi omega 0 x y z bar, psi omega 0 bar x y z bar, right? You just fix two variables. You can fix any of them. The first two is, yeah, I'm going to stop in 2 minutes. The z bar, right? You just fix the first two variables. You can do this because it's totally antisymmetric. So the change that you get here is going to be killed by the change that you get there. So I can put it here. It's going to be clear here if I write it in this way. The z bar, right? And what is this? This is, take this one, put it here. So it is just the same as trace of u gamma 2 psi 0 omega, right? It's the same thing as taking the trace of this operator. Okay? But what you see here is that if you want to understand how large this is, you need good information on what this vector looks like, right? And good information on what this vector looks like, what is it? It is knowing at the same time many eigenvalues of your random system, right? If you consider, so, and of course, just an upper bound, for example, knowing that the eigenvalues of the the eigenfunctions of the random system are decaying exponentially, will never give you any idea of what this looks like, right? It's just an upper bound, so you know that you have a bound on this, but you don't know how much you are going to change the energy by adding this interaction, okay? So, well, I stop here. Thanks.